Hello everyone, my name is Mike Patrick and I work for Red Hat. Over the past 2 years, I have been working with others in the community on improving support for checksum and segmentation hardware offload in Open vSwitch. Today I will present an update on the status of that work. This presentation will provide a concise overview of an explanation of the feature set, a history of the progress towards making these features more available in OVS, some scenario-based benchmarks to demonstrate the performance impact in realistic scenarios, and finally, a discussion of future work. Overview of the problem set. For the remainder of this presentation, I will be saying hardware offload, but it is important to note that I am not talking about TC, RTE, flow offload, or etc. I'll be instead referring only to checksum offloading, TSO or TCP segment offload, tunnel TSO, and the implementation in software of identical functionality in OVS. Furthermore, for the remainder of this presentation, I will only be discussing the Userspace data path. And when it comes to a lot of the TSO features that I will be discussing herein, they are considered experimental and they are disabled by default in OVS. They can be enabled by running the command in this slide and then restarting OVS. It is also important to note that this feature cannot be enabled or disabled during runtime. A restart of OVS is required. Furthermore, it is also important to note that when a vHostNet attached VM boots up, it negotiates feature support, including TSO, with OVS. These supported features cannot be modified unless the VM is rebooted. So if a virtual machine is booted before this command has been set and OVS restarted, that VM will still not be able to enable TSO offloading. Prior to OVS 3.2, offload support was very limited. OVS had some limited ability to handle packets flagged for segmentation offloading, but there was no software fallback in case that a transmitting network interface did not support this feature. This could result in dropped packets. Likewise, there was no support for TSO of tunneled packets, also potentially leading to dropped packets. And the checksum offloading support in OVS was not complete. There were certain circumstances where OVS might touch a packet's checksum instead of allowing the network card to calculate it. This all resulted in a lot of wasted cycles, most obviously in traffic that flows from local to local. This traffic technically didn't need to be modified by OVS at all, as long as both sides are properly configured. Prior to all the improvements that I will soon discuss, OVS might have even dropped a packet that could have just been handed off directly to the recipient interface. The lack of TSO support may have also encouraged users to increase the MTU of their local interfaces, like in containers, for when workloads would require a lot of local-to-local packet transmission. This is just as true for when physical NICs are in use. Support for some subset of these hardware offload features are now the norm, not the exception with modern network interface cards. Failing to account for these features can leave a lot of performance on the table and packets on the ground. Progress towards a solution. In August 2023, OVS 3.2 was released. This version improved tracking of layer 3 and 4 checksums throughout the life of the packet in OVS. This includes improved support and handling for checksums when a packet needs to be modified, for example, with contract. This version also attempted to detect offload capabilities and present them to the user throughout the interfaces table. Here is an example of what that offload information looks like. This is just a vEth interface attached to Open vSwitch with the NetDev Linux NetDev class. And we can easily see this interface supports UDP, TCP, and SCTP checksum offloading. It also supports TCP segmentation offloading, but it does not support any of the tunnel TSO features like Geneve or VXLAN TSO offload. In February 2024, we released Open vSwitch 3.3. This version contains the first release of tunnel TSO support. In this version, the user can encapsulate a TSO flagged packet with a UDP tunnel. Previously, this would have resulted in a dropped packet. This version also included a software fallback for basic TSO. However, the software fallback did not support tunnel TSO. So there was still a case that would result in dropped packets, including when a tunnel TSO packet needed to be encapsulated by a second tunnel, or if the interface did not support that feature. Just recently, in August 2024, we released Open vSwitch 3.4. We added the ability to disable checksumming of IPv6 UDP tunnels. This change might not seem related to the rest of the topics in this presentation. However, this is important because not all network cards that support tunnel TSO also support checksumming the outer UDP layer. In those cards, because there is no software fallback for tunnel TSO in this version, TSO would have to have been disabled or packets would be dropped. So disabling that checksum can yield a sizable performance boost depending on user deployment configurations. And looking towards the future, some more patches were recently accepted into the OVS main branch and are expected to be included with Open vSwitch 3.5. This version includes a software fallback for tunnel TSO when the transmitting network interface does not support it. This fallback can also be useful when the network interface does support tunnel TSO but doesn't support the outer layer UDP checksum offloading. That's enough dry stuff for now. Let's get into some practical benchmarks. The setup for the following tests wasn't designed to be a holistically realistic scenario, but instead to specifically show the impact of these changes in isolation. As such, these tests were run with the main branch of OVS on server-grade hardware, a Xeon CPU, Mellanox network card, However, I didn't make any effort in tuning the configuration to run on this hardware. I kept the MTU at a standard 1500 on all virtual machines, containers, and network interfaces. I also just used iPerf3 as the traffic generator, as opposed to a more advanced solution like Trex or Test PMD. So the numbers will be realistic for out-of-the-box applications, but not necessarily the most throughput that we could possibly squeeze out of this hardware. The following tests were run with both Userspace TSO enabled setting turned off and then turned on. This setting shows the impact of our TSO improvements. It's important to note that I'm not benchmarking the improvements to general checksumming from OVS 3.0 to present. These changes would have some impact when comparing with from old OVS to now, but the extent of the impact would be minor for these simple tests where packets aren't being significantly modified. And when it comes to some of the TSO tests, OVS 3.0 would have just dropped those packets. The first scenario involves sending data from a container through OVS out to a DPDK attached network interface. It represents the configuration of an application running in a container and sending data over the network. The container was attached to OVS via a NetDev Linux NetDev class. The NetDev Linux interface has a lot of limitations. It's not directly relevant to the topic of this presentation, but packets from this interface are handled in the OVS main thread instead of a PMD thread. This heavily restricts performance. However, here we do see a more than 4 times improvement in throughput simply by enabling TSO from 2 gigabit per second to 9 gigabit per second. The next scenario shows sending data from a VM through a vHostNet interface and to a DPDK attached network interface. It is very similar to the previous example, except the flow container has been replaced with a virtual machine. The flow data remains going out of the network card. As with the previous test, OVS was only configured with a normal action to switch the packets. The effect of TSO in this scenario yields a 3 times increase in throughput from 7 gigabit per second to over 24 gigabit per second. This scenario is similar to the previous one. However, now the packets are encapsulated in a UDP tunnel. This example is a lot more similar to what you would see when an application is being run in a cluster. We again see that a 3-fold improvement in throughput from 6 gigabit per second to over 22 gigabit per second. This scenario shows the local delivery of packets from one VM to another. OVS was reverted back to only switching packets with the normal action for this test, so the packets are no longer modified. This scenario represents what could happen for a workload that needs to move data from VM to VM locally on the same host. We see that the throughput has more than doubled from 4 to 11 gigabit per second. In this final scenario, I benchmark local VM to VM packet delivery, but without the VNet interfaces. Without the vHostNet interfaces. Instead, these interfaces were just set up as tap interfaces automatically by libvirt. While vHostNet is certainly the preferred option to connect a VM to the Userspace data path, a user might prefer to allow libvirt to configure and maintain the network for them for ease of deployment. And here we see a more than 3 times improvement in throughput from 2 gigabit per second to 6 gigabit per second. Now I'll discuss some future work. Currently, OVS has support for tunnel TSO with VXLAN and Geneva encapsulated packets only. However, I hope to add GRE support in the future. I'm currently working on this feature and intend to send a patch to the mailing list soon, so keep an eye out for that. It is also important to note that the Userspace TSO feature is currently considered experimental. We have encountered a few unexpected faults with this feature previously, especially related to flaws with network card support of this feature. I've made reference a few times previously in this presentation to network cards not supporting the outer UDP checksumming for tunnel TSO packets. We have encountered a network card that lists support for this feature but does not actually support it, and we have had to add an exception in OVS for this. As such, I would appreciate any reports from the community of your experience using this feature, whether it works properly for you or not, whether it has appropriate performance or not in your deployment. This has been my presentation. Are there any questions?
Okay, we have a question in the room. Hold on just a second. Mike is online to answer questions, so here we go.
Hello. So if I understood correctly, you just run iperf, one iperf, which did one TCP connection in one thread, right? And so the numbers that we are seeing are for one TCP connection, single threaded, right?
Sorry, I was muted. Yeah. So for this setup, those specific numbers were for a single PMD thread, a single iperf thread, and a single TCP stream. I have also done some benchmarks, and that wasn't just with one sample taken, of course, that was with multiple samples. But I have done benchmarks with other topologies, multiple traffic pitchers and catchers, and what I found was that the results were nearly the same. And as you pointed out, that was traffic in one direction, but of course we would expect that because we weren't, changing the for this test, modifying the MTU or anything else of the other side, the receiver in this case. If the receiver was sending packets, then we wouldn't expect TSO to show a significant change in performance.
Okay, any additional questions either in the room or online? Oh, we got one in the room here. Hold on just a second.
It's more of a comment. You can do that with full hardware acceleration, and then you get TSO from the VM side, and on the CPU side, you're probably going to have 0 CPU, and you can get line rate easily.
Okay. Are there any other comments, questions, etc.? Okay. Oh, sorry. Oh, we have one online. I'll read it out loud. Oh, no, it disappeared. Someone else read it. Who's in the chat? All right. Wait, I can.
I could read that if you want.
Oh, that'll be great, Mike. Thanks.
Flavio asks, does TSO work for user space and kernel data paths? So as I mentioned in the presentation, I was only talking about the user space data path. The feature is already implemented for the kernel mode data path.
Aaron, question from you.
Not really a question, just more of a follow-on comment. It's, yeah, mostly supported in the kernel data path, but for things like upcalls, we actually have to segment the TSO packets. So if there were like a flow that got expired, and then we have some TSO packet that comes through and have to do a miss upcall, then that will get segmented. So, but of course you're taking an upcall there anyway, so I wouldn't expect performance.
Yeah, well, we'd have to segment it, but at least the flow wouldn't get, or the flow in the packet wouldn't get dropped. So the main problem, but a significant problem with the user space data path up until very recently was it would just drop packets.
Okay. Any additional questions? Okay, well, let's thank our speaker.